All right, what's up, divas? So I was doing some OChem review because I'm prepping for the MCAT, and I figured I learn best when I explain to groups of people. I don't know, maybe that's just my excuse to socialize because I get bored pretty easily. But what I figured is because I feel like I learn better when I'm explaining things and when I'm talking to people, I'm just going to record my study sessions so I can pretend like I'm talking to someone, and then I'm going to post them. Maybe you guys will find some use out of that. Maybe you won't. Doesn't really matter too much because this is more to help me than anything. I'm not even sure if I'm going to upload the videos. But today I wanted to start with electron energies. I think electron energies are a pretty good place to start because it kind of lays the foundation for a lot of the other concepts in OChem. And I think that's where most OChem classes are going to start. At least that's where mine did. So I don't know, maybe that's just a bias that I have. So when we're talking about electron energies, we're basically just talking about how excited is the electron. Also, a couple things when I write that E thing, that's electron. I figure like 99% of the people that see this are going to know that just because you've probably taken other chemistry classes if you're taking OChem. But I don't know. I'm gonna try and keep everything as simple as possible because I don't want to get too in the weeds with explanations because I know there's like exceptions for everything and all that stuff. But this is just going to be like a bare bones explanation of all these things. So when we're talking about how excited these electrons are, that's important because that's going to kind of play into chemical reactivity, which is going to be lower down on that page of definitions. Because if you can think about it, when you have electrons that are going to be very, very excited, they're going to have a ton of energy, they're going to want to react with things, right? They're going to want to form bonds, and it's going to be much easier for them to do so compared to something that's at a lower energy state. Because if you're at a lower energy state, I mean, just think about it, right? Like if you meet someone that's low energy, they want to sit on the couch all day, they're not going to really want to do anything. But if you have someone that's high energy, is always bouncing around, they're more likely to interact with other people. At least that's how I imagine it. I also think of them as like more spicy, like spicier electrons or higher energy electrons, but maybe that's just how it clicks in my mind. With electronegativity, it's just referring to how tightly the atom holds on to the electrons. And that's going to kind of play into ionization potential, which we're going to go over next, because I feel like that's kind of important. But before I do, I want to switch tabs over here and switch to the periodic table. Again, this is another thing that I figure like 99% of you will know. But when it comes to ionization potential, when it comes to electronegativity, it's going to increase up and to the right. So going to that top right section of the periodic table. But in case you didn't know that, now you do know that. And then we're going back to ionization potential. What that's essentially referring to is how much energy you're going to have to put in to remove an electron from that molecule or atom. It's basically like, if you think about it from the perspective of electronegativity, right? If an atom is holding really, really tightly onto an electron, it's going to require a lot more energy being input into that system to pull that electron off of it. Down. All right. And then that's just the super basic breakdown of some of the concepts that I think you should probably know. And I actually want to jump to the end of this list because I think this is probably a better question to start with. So we have lithium, and then we have two lithiums bound together. That's what that line means. That's just basically referring to two electrons because each of the lithiums will have basically the one valence electron, and then when they bond together, it's going to go and they're going to be shared between the two atoms. And the question in this case is, which electrons are higher energy? And a general rule that you can follow is if it's in a bond, it's going to be lower energy. And that's just because if you think about it from the perspective of like you have your two atoms, right? And then actually maybe I should just draw all three of these for perspective. So this would be like just your plain lithium with the one valence electron. And then in this case, you're gonna have your two lithiums that are basically bound together. When you have this situation where there's a bond, each of these electrons is going to be essentially influenced by the positive charge in the nucleus of each atom. So in this case, we have the electron being influenced by the one nucleus, but over here when we have the bond, we have the atoms being influenced by the lithium on one side and the lithium on the other side. So you basically have two positive charges that are basically working together to stabilize those electrons. And by stabilizing the electrons, they're going to have a lower energy overall. So in this case, because this lithium isn't in a bond and it's just basically by itself, this one is going to be the higher energy electron. And then the one in the bond is going to be the lower energy electron because it's going to be more stable. And obviously, if something is going to be more stable, it's going to be less reactive. And then we can go ahead and jump back up to the top of this list. So then we have a potassium versus a chlorine. And in this case, we're talking about which one is going to have the higher ionization potential. And if you guys just needed a quick refresher, ionization potential is the energy needed to basically remove one of the electrons. So which is going to require more energy to peel off one of the electrons in this situation. And in this case, if we refer to the periodic table, we have our potassium and we have our chlorine, basically on opposite sides of the periodic table. And in this case, we know that the chlorine, based on its location on the periodic table, is more electronegative. EN is my abbreviation for electronegativity, if I didn't mention that. And because it's more electronegative, it's going to have basically more of a desire to tightly hold on to those electrons compared to potassium, which is essentially all the way on the other side of the spectrum. And because of that, the chlorine is going to have the higher ionization potential or ionization energy, whichever one you prefer to use. And then jumping to the next one, we have a fluorine atom versus water. I'm pretty sure you're not going to find fluorine by itself most of the time. I think it's going to be F2, but I think this is a good example nonetheless. So in this case, we're going to have the fluorine as being more reactive. This one is probably going to be one of the easier questions because in general, like I feel like whenever I've come across questions involving fluorine on exams and on homework assignments, it's always going to be the most electronegative, it's going to be the most reactive, all that good stuff, except for, I mean, I guess maybe like really, really specific cases, but I'm not going to dive into that because I don't really care to, and that's too nitty gritty for me. I don't want to niche down that much. So the fluorine is more reactive. It is also more electronegative. And the other thing to think about in this case is if you didn't just want to go off of the electronegativity and you kind of wanted to look at these atoms and I guess the water molecule together and kind of understand, all right, but why is that actually happening? Why is the fluorine going to be more reactive? Well, with the fluorine, if you look at it over here, we're essentially having just the one electron by itself. It's not paired up with something. And then in this case with the water, it does have lone pairs of electrons, but they're paired together, right? So because they're paired and they're stabilized by the hydrogen bonding that you're going to find in water, it's going to be more stable in general than fluorine will be, because that fluorine with just its singular, electron that's vibing by itself and it's not a pair or something is really going to want to bond with something else. And therefore it's going to be more reactive because in order to basically bond with things, it's going to need to react. Next, we have which is going to be more reactive in terms of NH3 versus CH3. And actually one thing that we should note is in this case, it is going to be an anion, this CH3. And the reason for that, damn, that is really loud. I'm gonna give that a second to pass. But in regards to CH3 having the negative charge attached to it, when you have anions, because it's a carboanion, it's generally going to be more reactive because you have to think about this carbon is essentially going to become a nucleophile. And if you aren't aware, the nucleophile is basically its tendency or its desire to donate an electron to an atom that needs it or is deficient in it. I think that was the word that my textbook used, but I didn't really like the word deficient because it just seems weird when I'm thinking about like inanimate objects. And because of that, this CH3 minus is going to be more reactive. It's going to be more electronegative, which means that it's going to hold on to the electrons tighter. It's going to require more energy being put in order to break off one of those electrons, whereas this carbon is less electronegative because it's further to the left on the periodic table, which means that it's going to require less energy to be input in order to basically remove one of its electrons. Let's see, what else do we have? This is going to be the last question. We have chlorine, and then we have a chlorine anion. So this is also a good segue from the previous question, because when we have these two, essentially the only difference between them, the reason it has the negative charge is because we have that extra valence electron that's coming in, which is why it has that negative charge. And the chlorine, the anion, is going to have a lower ionization potential. And the reason for that is because when you think about stability with atoms, there's only really one way to stabilize an electron, at least from what I've learned so far. It's going to be the protons that are in the nucleus, and the nucleus is basically like attraction on them to help stabilize them. So when you have electrons that are basically, overwhelming, I guess is the word that I would use, the nucleus, you're going to have basically another electron that's not supposed to be there, and because it's being added, it's much easier to remove because it wasn't there to begin with. Its natural state is only going to have 7 valence electrons, which is, the orientation on the left, and by adding that extra one, it's going to be a lot easier to remove it because that's not the way that it naturally wants to exist. That's not the way that it's typically found. It doesn't come with 8 valence electrons. And I think that is where I'm going to wrap this up. Yep, that's the last of the questions. So that's just a quick breakdown of electron energies. Hopefully it was helpful. We'll see if I end up posting any more videos or if I even post this one. But we shall see.